The Great Ideas of Classical Physics by Professor Stephen Pollock. Welcome, my name is Stephen Pollock, and this is a course on the great ideas of the classical physics. I'd like to jump right in by taking apart these words, and let's talk about what I mean by great ideas. What is classical physics? Let's start with the easiest perhaps. What is physics? Physics is a study of the natural world. It's a study of the physical world and the world we live in. It's experimental science, and it's really the heart, the core of all other experimental sciences. Physics goes beyond just a simple description of the nature. It's an attempt to unify a broad variety of the phenomena that we observed in the world, both the natural world and the technological world. We are looking for the underlying principles, the explanation and the predictions. We would like to be able to really understand the world around us, the measurable things in particular. Physics studies matter and energy, space and time. It studies particles and waves, and forces and motion. These are a lot of words that we use. We have a deep, intuitive sense about what those words mean, and part of what we are going to be doing in this course is to start looking carefully at each of these words. What do I mean by energy? What do I mean by force? How would I define that in a laboratory and measure it? And what is used it? How does it help me to understand things about the world? So we're gonna spend some effort to try to be careful about our definitions. We will create what I called operational definitions, which are things you can do in the laboratory, and so that we know precisely what we mean by these words. Ultimately, we are always looking at the world. We are looking at the things. Physics is about stuff. How does it move? Why does it move? How does it work? We are trying to look at the underpinning principle to understand how and why things behave as they do. You could distinguish the physics from other sciences. But in some respects, the boundaries are artificial. Is it physics or is it chemistry? Well, chemistry, I'd argue, is a special kind of a specialty arising from the physics in which you study a particular aspect of the world, materials and how they mix together and combine to form different materials with different properties. Of course, there are proper people who are chemical physicists and physical chemists, and for those people, this distinction is very blurry. We are going to zoom in on the core idea so that we can then move up if we want to and understand other fields, chemistry, biology, geology, astronomy, and all of these other disciplines, scientific studies. They are under my broad definitions, physics. They are attempts to understand the natural world. Living organisms for the biologists are a part of the natural world, and so you could argue that that's physicists. Sometimes physicists will make that argument, but we are going to look at the basic here. We look at the rules of the game, and we will try to understand what the key players here. What the key players here. What objects can we think about that will help us to understand a broad variety of the other objects, and what rules do we need to understand in order to understand as much as we possibly can about things that we see and things that we measure. If you watch an Olympic high diver, they go off and they do spins and flips, and it's a complicated system. It's clearly a physical system, and as a physicist, you might want to be able to describe it, predict what's gonna happen next, and make sense of it. What we will often as a physicist is idealize and simplify, I will talk about point-like objects throughout this course, like that Olympic diamonds whose center of mass acts like a point-like object acting through the air, so you can make a joke about it. There is a physicist who is trying to help the farmer and says, let's consider a spherical cow. It is a joke, but on the other hand, and it depends on the little bit on the question that you are asking. If the farmer wants to know how many cows will fit in the barn, it may not be a terrible approximation to assume a spherical cow. If you are interested in the more milk production, then it's probably not the most fruitful approximation. In the end, we can always go back and add in the complexity. Okay. But we will always start with the basics. Physicists are, in some respects, simpletons. Simpletons. Neutron, electron, simpletons. Wow. And what else? There is something about the related to genetics. なんとかトン or something with tongue. What? I forgot it? Can't believe that. Well, anyway. I love to think about a point-like object obeying fundamental laws. Let's neglect friction. Let's not worry about complication. Now, if you hear that and you say, what do you mean neglect friction? Friction is everywhere. It's a part of the world. How could you possibly understand the world if you neglect parts of it? My argument is, well, first, we neglect it. We go to the core ideas, what is going on, then we add it back in. And physicists certainly don't neglect frictions in the end. It's just another force among many forces, and if we understand the nature of the forces as a concept, then we can add in the specific ones as we wish. Oh yeah. It's all about the breaking down and integrate together. This is a way of science, This is really one of the central ideas of their discourse, to try to break things down and look at the underpinning story. Yeah, so cool. That's really what I mean when I talk about the great ideas. The great idea of the physics would be those essential fundamental principles, the guiding core principle that we need to understand. Now I can't just list the first. I can't just list them for you. I wish I could, but first of all, the list is essentially everything we are going to talk about, and maybe even more in this course. Every idea in the history of the physics has, in their certain sense, been great idea. Yeah. Furthermore, what was a great idea in the one period of the history developed and evolved, and it turned into the other great ideas, and the original one lost some of its everyday usefulness or necessity. Yeah. It's still an underpinning story. It's just not necessarily a great idea depending on the particular question that you are asking. So in the end, what we're gonna discover is that the great idea of the physics are simply the deep ones, the principal one that we are interested in, and that's what we're gonna focus on. Yeah. Let me give you an example of the great idea of physics. One of the truly spectacular ideas, which arose historically all around the 1600s, was that the world can be understood by doing experiments. It's an empirical question, not a philosophical question. Before that, it might seem obvious to you that if you want to understand if you understand the world, you should measure it and do experiments on it. But that's definitely not been the case for much of human history. People just philosophized, and what we today call physics was once upon a time called natural philosophy. It was a philosophy of the natural world, and people would argue, well, I believe that the world should be this way, and I believe that the world should be such a different way. Then their arguments were often intense and deep, and they were grounded in the elements of the observations. But they weren't thinking about making concrete measurements and then testing their ideas. The experimental method of the experimental method or the scientific method turns out to be one of the truly spectacular, successful, powerful, and great ideas in the history of the human civilization. Let me say a word about the scientific method. This great idea really has many pieces, and you can define the scientific method in a variety of the ways. I'm going to go for a simplistic but essential definition of the scientific method as a set of ideas. You begin in the science by observing. Look at the world, be curious. I would argue that curiosity is a part of the scientific method, but that's not enough. That's not enough to be a science. That's not enough to do a science. You have to stop and hypothesize. You try to figure out what are the deep ideas, what are the organizing principles. Can we connect this observation with a very different kind of the observations? And if you do that, then you will realize that you have to go back. You have to think about your observation. You have to do experiments. You have to make measurements. There is a cycle in the scientific methods. You observe, you hypothesize, you theorize, you experiment, and it's really not an orderly process. Yeah. It can be very messy in real life. Sometimes you do things in a funny order, but ultimately this scientific method is grounding. When you believe something about the world, you have to be able to test it. You have to think about the consequences. Once you've made a hypothesis, you look for the other situation, broader application of this idea, and you test them. You often do this with mathematics. Mathematics is really just a tool to formalize logical consequences. Mathematics is not necessarily about mathematics is it's not necessarily about a formula and plugging the numbers in. It's more about relationships. Formulas tell stories. They say, if you change one thing in the world, then another thing will respond. Mathematics is about cause and effect, and if you want to understand the world, if you want to understand cause and effect, mathematics is a delicious and powerful tool. It's definitely part of the scientific method to make your theories quantitative, to make measurements that you can compare with the experimental with, and then make numerical prediction from.